In this video, I would like to talk about the preparation and reaction of esters. So there are two different ways to form an ester. One is to take a carboxylic acid, make the acid chloride with thionyl chloride, and then treat this with an alcohol, for example, methanol, to give the ester. We call this methyl. That's the part that came from the alcohol. And acetate. That's the part that came from the acetic acid or the acid. The mechanism for this, as we discussed previously, involves methanol with a neutral nucleophile. And this guy here will attack the carbonyl carbon. And you'll get this infamous tetrahedral intermediate. Now the tetrahedral intermediate immediately collapses. There's no proton transfers at this stage yet. So the negative charge then comes down and kicks off the chloride. Always use your lone pairs. And then what you have is a deprotonation step. So we've got our ester that appears to be protonated, and then something in solvent, in solution, a solvent or a water molecule or an alcohol like methanol molecule can deprotonate, and this will give you the product. Okay, so that's AED for an acid chloride going to a ester. The other way esters can be formed is with a neutral carboxylic acid. Okay, and I like to say acids require acid. And so this is a carboxylic acid, and if we treat this with methanol, it requires a drop of sulfuric acid catalyst. Up here we don't need that. There's no acid required because the acid chloride that you're starting with is extremely reactive. Now this carboxylic acid here that we're starting with is not too reactive, so we need an acid catalyst to push this equilibrium to the right. And so we get the ester. How does that work? We take the carboxylic acid, okay, and we protonate one of these oxygen atoms. You could protonate either, but the one that will lead you to the product correctly is to protonate this one here. Okay, generally you always protonate the carbonyl oxygen lone pair. Now methanol is going to come in at this stage and attack the carbonyl carbon. And you get, once again, as you can imagine, this tetrahedral intermediate. And it's kind of confusing because you have all of these oxygens bound to the same carbon. Okay, so it's a kind of a cluster of things here. Now what we have is we have a situation where we want to move this proton to this oxygen so that we can kick off the water, which is a good leaving group. We can't kick off OH minus. Okay, we can't kick off OH minus. It's not a good leaving group here. So what we need to do is continue with some proton transfers. So we have methanol, which is a neutral solvent, right? But it's going to deprotonate here. So that hydrogen's gone now. And let's draw in these other guys here. And now we have these lone pairs that can pick up a proton from protonated methanol or the H plus I'm just drawing here. Okay, and this will give us a intermediate that looks like this. Now, the whole purpose of doing this is to ensure that we have neutral water that's going to be a good leaving group here, okay? So now you use lone pairs. You could use either of the two lone pairs. You could use these, or you could use these. I'll just use this guy here, okay? And so that's a protonation. This is elimination. So you lose water in this step. And what you have is a protonated carboxylic acid. Okay? The proton could be attached to the carbonyl oxygen or to this, oxygen down here. It doesn't matter. And then what you want to do is take a solvent molecule. In this case, it's methanol that we're using to deprotonate that final molecule. D for deprotonation, to give us the neutral ester. So that's PAD, PED, PAD-PED. Okay, PAD-PED is the sequence of events. Okay, a little bit longer compared to the acid chloride. The acid chloride up here was AED. Okay, direct attack can begin because acid chlorides are so electron deficient and so reactive. Okay, so when we think about what other reactions carboxylic acids can undergo, esters can undergo, we can also think about reductions. So lithium aluminum hydride can react with lithium aluminum hydride to give you two equivalents of an alcohol. This alcohol from the acid and this alcohol from the alcohol part of the ester, okay? So let's look at some other complicated maybe situations. If we have something like this, okay, and we treat this with lithium aluminum hydride, water. I'll draw the product fractions in yellow. So there's 1, 2, 3, 4 carbons. So we have a 4-carbon fragment, primary alcohol. And in white here, we have the other alcohol that's formed. That's going to be isopropyl alcohol. Okay, and you can see how the OH is bonded to the middle of this carbon chain. Okay, right here. All right. So for your practice, well, let me give you one more example of a cyclic guy here. Cyclic esters are called lactones. And if we treat this with lithium aluminum hydride, what you want to notice here is that this carboxylic acid, right, it always changes to a primary alcohol. Okay, you can see the yellow dots here. So what you're going to form is a primary alcohol at that carbon. Now in white here, we have all of these carbons all bonded to one another still, right? And then what you'll notice is that this bond here, we can call it the ester bond if you want, it breaks. So we're going to break that bond and we just make an alcohol. Okay? So in this case, lactones or cyclic esters form diols. Okay? This is 1,4-butane diol. Okay? Now, esters can also react with Grignards. Well, first, let me just say that there's a mono-reducing agent for esters, and Klein likes to use lithium triterbutoxyaluminum hydride for acid chlorides, and diabal, I guess, for the ester. So here's diabal, okay, and you'll notice from the abbreviation here that it only has one H. So what you get from this chemical reaction is an aldehyde and an alcohol after you know, add water to this chemical reaction. The mechanism for this we've reviewed. Whenever you have hydride, you go ahead and attack the carbonyl carbon, and here, contrary to what we've been talking about, the negative charge is a good leaving group if you have this situation, a negatively charged intermediate, and what you'll get is an aldehyde, and that stops here, okay? If you have lithium aluminum hydride, more hydride attacks and you get the alcohol, okay? So basically you do that. There's the OCH3, you know, that gets worked up upon hydrolysis of using water as the solvent, right? So here we have methoxide that hangs out, and then in step 2 you have water, and that gives you the other reaction product, okay? So you get butanal and you get methanol as 2 reaction products, okay? So another reaction that I want to talk about is Grignard's, as I alluded to. So if we have a ester, let's say this one here, and I add excess Grignard, and then I add some water at the end, what I get is the same type of product as before. You know, we have a primary alcohol, but instead of hydrogens being added here, you see I'm drawing H's. Instead of hydrogens, we're going to be adding whatever alkyl group the Grignard is supplying, okay? And this gets blown off, and you get this alcohol from the ester, okay? Normally that's the byproduct, but it depends on what kind of reaction you're doing, okay? Normally you're operating on, you know, the carbonyl side of the molecule to make more complicated alcohols. How does this work? Well, you have the ester, as we mentioned, and this is exactly the same as lithium hydride. So lithium aluminum hydride does the same mechanism, okay? So you just might make a note of that. So we have CH3 minus, okay? Remember, that comes from the Grignard. So we attack the carbonyl carbon. I accidentally dropped off my oxygen there. Okay, so there's that oxygen. So you want to kick off the negative charge. Okay, and what you get is a ketone. And we've learned before that ketones can react with Grignards, and that's why we say excess, right? That means we have lots of equivalents, more than 2. The first equivalent here attacks the ester. The second equivalent here attacks the ketone. So go ahead and swoop that in. Electrons go up towards the carbonyl oxygen once again. And we get a alkoxide. Remember how oxygen, an alcohol that's missing a hydrogen, is called an alkoxide. Okay? And this is a tertiary, well, I'll show you the product and then we'll discuss tertiaries. So then what do you do at the very end of this reaction? That's where you add water. Okay, so water you don't use until the very end. And basically it serves the purpose of delivering a proton to your molecule to give you the neutral organic product. Okay, so I'll just draw it in shorthand notation here. So this is a tertiary alcohol. And that came from the carboxylic acid. I'm sorry, it came from the carboxylic ester, or the ester we say. Okay, and so it's this port of the molecule that you're using. Okay, so you really want to understand this. Aldehydes, and say LAH, what's the product? Ketones, LAH, what's the product? Okay, esters, diabal gives you the same exact product. And carboxylic what do you call it? Sorry, that's not correct. This diabal will give you the aldehyde. Okay. Lithium aluminum hydride will give you an alcohol. Lithium aluminum hydride here will give you an alcohol too, but you want to draw these in and think about those. And LAH will give you an alcohol as well. Okay. Maybe that's a terrible review. Let's draw some other things here. Okay. So if we have let's draw a simpler molecule here. Okay, and we treat this with lithium aluminum hydride, water. Treat this with diabal, water. And we treat this with excess, we'll do ethyl magnesium bromide here, and water. Okay, so let's review what we've learned here. Okay, so lithium aluminum hydride will deliver, right, 2 hydrogens to this carbon atom. And what we get is a primary alcohol. And if we just look at, carbon likes to have 4 bonds. Those 2 hydrogens came from the H, or the hydride from lithium aluminum hydride. Diabal delivers 1 hydrogen to the carbonyl carbon. Okay. And once again, we normally draw the hydride, the hydrogen of the aldehydes. Okay. And what about ethyl magnesium bromide? What does that do? That delivers 2 ethyl groups to the carbonyl carbon. So we're going to have an ethyl, and we are messing up here. That should be a single bond, and that should be an OH group. Okay, and there should be another ethyl group. Okay, so I hope by this slide here you can kind of see the overview. Diabal has only 1 hydride in the formula, right? So you form one of those. And lithium aluminum hydride, if you write it out, and remember what it stands for, you have multiple hydrides there. So you can add 2 hydrides, 2 hydrogen atoms to the carbonyl carbon. And Grignards work the same way. You form 2 ethyl groups, okay? What I'm showing you here on the slide here are the primary reactions for the carboxylic esters, or the esters, that you should be familiar with. Now, in the lab, we're going to be talking about hydrolysis of esters. And the idea here is that if we have a carboxylic acid and methanol, This is in equilibrium with the ester and water, and this is acid catalyzed. So if you think about Le Chatelier's principle, if you pump up the concentration of water and add a whole bunch of water here, you're going to shift this equilibrium to the left, and you're going to form a carboxylic acid and methanol as reaction products. And that's called hydrolysis. Hydro means water, and lysis means to break. So if you take any old ester and you add bunches of water and H+, you will form a carboxylic acid and an alcohol. Okay, so you just want to split it up right there. The mechanism is quite complex and lengthy, and I won't go over it, but I'll give you one practice problem. Draw the products from this reaction here. Let's make a super interesting looking ester here. So if I add H2O and H+, assume that the double bond doesn't react, draw the two products here. Okay, so that's a brief review, overview, kind of looking back at the different reactions of esters. Okay, thanks for watching.